Hello, how are you doing? We're gonna work with the lab today, so you want to take a look at that? We'll go over the lab, okay? Good, thank you. I'm glad it's Thursday. I have a machine learning project that I have to work on tonight for my class tomorrow with Georgia Tech. But yeah, I'm good. Progress in the week, productive week. I'm thankful. I hope everyone's doing well. I hope you're doing well. All right, so let me get to the screen share and we'll do some LC3 now. Okay, so we'll go ahead and get started at 6 o'clock. Welcome back. Today we're gonna do lab 10. And so next week we're not gonna have a lab, but so I'll talk a little bit more toward the end of what our plan is gonna be next week. So I want to give you some time to work on your project. And then I do have a field trip that's coming up, so I will remind you about there's not required session for lecture down the line, okay? So for today, we are going to do random number generator in LC3. The code, you will find it on the screenshot and you will go through the assignment document. So I'm going to open that up now. So in this program, we are going to use LCRNG. That's going to be linear congruential random number generator. We are going to have a seed that's going to range from 1 to 32766, and it's going to be at location hex 3100. We are going to generate 20 numbers. It's going to be interval between 1 to 2 to the 15 power minus 2. And so for the equation, we have x of n is a times x of n minus 1. So this one have some recursion plus c mod m. Okay. Now the a is going to be the constant, c is going to be the constant, and we're going to do the modulus of m. These will be integers. And so they are going to be chosen and fixed. So make sure we keep this in mind. We're going to have the given seed at hex 0. So your seed is always going to be the same. So this is a pseudo-random type of generator. So it might look random, but it is not truly random because it's pseudo, right? Because we're seeding at the same position. So please keep that in mind. And so it's going to generate values in the range of 0 to n minus 1. And eventually the sequence is going to repeat itself. So it talks about that there. When you look at this equation, we know that we need to apply multiplication as we are going to take the constant a times x of n minus 1. So we are going to call on the mult function. We're going to also use division function or subroutine div because of the modulus, and we're interested in returning the remainder from the division. So these two you already seen from the earlier lab. Now, for this program, we are going to take a look at how it could be having overflow in the case where C is 0. So we want to control the overflow using Shrage's method 1. And with that, we need to implement the criteria like this. So Q is going to be m divided by a, and R is going to be m mod a. And so that can also be written like this. If it is greater or equal to 0, we're going to take a times x mod q minus r times x divided by q. And otherwise, else, we're going to implement a times x mod q minus r times x divided by q plus m. And so we are going to look at how we can work that into the algorithm of our program. And we are going to try to make sure we implement the condition in that r is greater or equal to 0 and r is less than q. So this allows you to kind of see the pseudocode and how we would implement the algorithm. So earlier, we know that a is going to be the constant. And so based on Shrage's method, for this, we are going to initialize a as 7, as an integer 7. And your m is going to be the maximum value in the range, which is 2 to the 15th power minus 1, or 32,767 instead of 66, because it's minus 1 instead of minus 2. And x is going to be 10. So this is going to be your seed that's given. We're going to implement q is going to be equal to m divided by a. So we would take this value divided by this. So once you initialize these variables and bring them to the registers, we need to operate the division to return the value for q. Then we also need to find the value for r, where r is going to be m mod a. So here is where we would return the remainder. That will be r. Then we're also going to implement the loop. For 1 to 20, it's going to do x is the Shrage's method, right? A times x mod q minus r times x divided by q. If x is less than 0, and that if that's the case, then it's going to be x is going to be x plus m, and we're going to return x. Okay. So this is kind of the main components of our program. Now, in the next section, it talks about your 2's complement for the bit arithmetic. And so for the largest possible m is going to be 2 to the 15th power minus 1. And we see that in the listing 8.1, which is 32,767. Now, using this value as a maximum value for a non-repeating sequence, you're going to go from 1. It's going to generate value within this range between 1 and 2 to the 15th power minus 2 before it repeats itself again. So it should have different values from this range generated. So we want to look for that when we output. Okay. And so for the random number 1, it's chosen that your a is initialized at 7. And so your seed where x of 0 should never be 0. Okay. So this is why we see this, that where we have to implement if it's greater or equal. Okay, so we need to make sure that the first one cannot be 0. And it should be any number starting with 1 to the 15th power minus 2, or 32,766. So our random values needs to be in this range. Then this is kind of the layout for your program. And it tells you the assembly command out, which is shorthand as trap vector 21. We need to output this onto the console. And so we would need to ASCII convert. And in order to output, you have to make sure that it goes to register 0 first to do the out. So they give you a little bit of the foundation for the code, right? In this case, we see that it's a 2 complement of register 3. We're going to load the label minus to register 0, so that way we would output. And then we would load the offset to register 0. And we would add these together and then we would output. So this is how you can represent a negative sign on the ASCII with the digits. So if I wanted to say negative 400, right, I would have the minus symbol to indicate the negative symbol, the minus label for the minus symbol, and then the values. Where I combine it, I would be able to show my characters as negative values. And so with that, we need to fill. Okay. And so the offset, in this case, we're using hexadecimal. So it's hex 30 instead of decimal 48. But for your project, you can use either or. And with the requirement, we want to also look at stack. So in this one, we are going to output decimal values as 1 is 1. And so it tells you here that we can obtain the digits by successively applying mod 10. So whenever that you're working with a number system, let's say we are using decimal system, because there are 10 values in that, you can apply modular arithmetic with that. So you would do mod 10 to really truncate the value so that way we can obtain whether the remainder to represent the digits. And so in this case, when you're looking at this, it says, for example, if the number that we would like to output is 537, that will be hex 219, we would apply the procedure in the digits 735. The reason why is you are pushing in 7 last and 5 first. So that way it would display the opposite in the order. So if I push in the 5 last, it's going to be actually 735 instead of 537. So we have to look at the order on when we push the digits onto the stack. Remember that, last in, first out. So if I push in the order, so 7, that's going to be the first one that comes in. That's going to be the last one that pop out. Then the 3 in the middle, and then the 5. So the 5 is on top. So the 5 is going to be seen first. Okay. So we have to do the reverse order so that way we can represent from left to right versus right to left. Okay. For the push. Any question? Okay, so the listing 8.3 kind of lay out some of your output for the stack. So if we want to use left as n and the sign as 1, if n is less than 0, then we would have it sign is negative sign, so we can negate it. Now, if left is negative, and if left can be, once it's signed it's going to be a negative value. If left is 0, then your digit is going to be 0. Then we're going to push the digit. If left is not 0, then we would take that value, we're going to mod it by 10, so that way it would generate the digit. And then we're going to push that digit next. Then we would take left divided by 10. If the sign is less than 0, then we would output the symbol that represents sign, which is what we said earlier about minus. And we want to also check to see if your stack is empty. I think last week we talked about stack where we would use an indicator to determine, right, whether your stack is empty or not. So that will be a register to see if there's a 0 or a 1. And so if it is not empty, then we would pop the digit and we would output it. If it is empty, then else, right? In this case, then we don't. Okay, so this is where we will be able to check our stack. So how do you implement this? So we would use label like push or pop and is empty. Push is gonna, in that section for the label, we are gonna push the content of the register 0 on the stack. For the pop label in that section, our instruction should allow us to check the top of the stack in register 0. And then if it is empty, then we're going to return 1 in register 0. So is empty returns 1 in register 0. If the stack is empty, then and 0 if the stack is not empty. So it would have 1 if it is empty, that's true, and 0 for false if it is not empty. The register 6, its job is going to be pointing to the top of the stack. Which value is on top, which value is last pushed in. Okay? And because we're writing a stack, it's going to be at hex 4000. This is a region of memory that we would use base for the stack. This is not to be overwritten for the stack. So this is where we would start. So you would initialize R6 for that region of memory. Then for R7, this is used to store return addresses for the call subroutine. And for is empty, that should be always called before proceeding to pop. So you always want to go to this label to check if it's empty or not, right? We talked about if it is empty, it's going to have 1, right? So that will check branch for positive. If it's not empty, branch for 0, right? So if it's not empty, if it branches for 0, check true there, we're going to pop. And so it would look something like this. Okay, you're gonna load R6 with base, where base is filled with hex 4000. And you are gonna use push as a subroutine. So you're gonna jump to subroutine push and then halt. So remember, base is filled here. And for the subroutine, we can define it. We would add R6 with -1. So we're going to move top of the stack up. And the term up here is kind of misleading because you have to think about how stack is growing downward, right? So you're actually moving down. Okay, so subtract 1. And then we're the authors of the book and the lab manual, they like to use store. When you see it like this, it's like copy. Okay, we talked about this in the lecture. So when you do an str R60 and store it to register 0, it's the concept, the result of this is like the copying. So I'm taking what's in R6, right? With 0, I'm going to store it back to register 0. So store R0. There. And then we're going to return. For the pop, we're going to load R6. When we push, remember that when we push in, it's going to move down 1. When we pop, we're going to move it back up. So you're going to add. So you're going to add the positive, and then for the push, you add the negative. And then return. Then is empty, we're going to load empty to register 0, right? And we would use that because the assignment called for that. So we would use register 0 to check. And then we would take the empty label register 0, add it with register 6, because R6 is the pointer for the top of the stack. So you add them together and put the result in register 0. And here is where you're going to check to see if it is empty or not, right? So if I branch for 0, then I'm going to send it to is. And then I would take our 0, add it with 0, and put it back for 0, and then return. So this is the else. Okay, if else. And then for the if statement for the branch 0, we're gonna clear it, and then we're gonna add the 1 to it. Okay, because remember, we would have a 1 if the stack is empty, 1 for true. So, and then return. And for this, we would basically fill it with hex C000, which is equivalent to negative hex 4000. And that will be the end. So this table represents the sequence for the random numbers that's generated. Okay. Now you should have numbers that are different in that range until it ends, until the end of the range. If it's coming back to the beginning of the range, then it's going to repeat the number. They should be different if they are only in that one range. So I need you to run the program, right? You should be able to output the number, test the program. So our program is hard-coded in with these values. So you're going to have A is 7, M is 32767 already. That's part of the algorithm. So after you run the program, I need you to answer 1C. How would you adjust this program to display more randomly generated numbers? Can you display more? It should be if you're using that equation, right? So how can you, this one is going to generate a certain number or a certain amount of numbers. We can probably change our code to have more values displayed, basically. Explain how the subroutine are used on the stack operation. You got a lot of it already here and in the explanation that I just went over, so you can follow along with the code as well, right? We talked about the push and the pop and how we check for the empty and so on. Any question?
For the push, you're going negative? You're going down?
Yeah, stack grows downward.
Okay.
Because if you think about, remember we talked about the coin, right? When you push, so when I push one coin, I push it down. Then when I push the second coin, the first one gets pushed down one. Okay, because when you're looking at the memory array, the address of the memory array, you're going to move down to the next one and the next one as you add more values. And then when you pop it, it's going to move it back up. Stack always grow downward. Okay. But in here, they talk about push as, you know, when you subtract it, stack up. But, you know, so if you're looking at that way, because if I reverse the analogy, like if you're stacking plates, right, one on top of the other, right, it's going up this way, but really it's actually pushing down, your stack growing downward.
So would a queue go upwards then? Or how does that work?
Like for, you mean a data container?
Yeah.
Data container, if you do a queue, basically what that does is it's a pointer to where your head and tail would be.
Oh, okay.
You know, so you're going to have a head and then it's going to link to the next one and the next one and the next one. And then at the end of the tail, the pointer, so the end of your, whatever the container, then what that does is it's not going to have any kind of link. So it doesn't point to the next, I forgot what they're called now, but you get the point, right?
Yeah,
Now,
it'd be like
if you,
null.
yeah, that will be a null. But on the doubly linked list, you're gonna have to link it back to the beginning, so it's circular. Mhm.
Oh, okay.
Yeah, so this is a little different in sense where it is a container, and for the stack, right, as you push it in, think of it like if you're subtracting one, it's gonna move to the next address, right? Move down
Yeah.
to the next, and then when you pop, it's gonna move back up.
Yeah, that makes sense. Thank you.
You're welcome. Okay, so let's take a look at the code. You can find this on the screenshot of the assignment page. I think I have this on Word. So I'll use this because it's a little larger. Okay, so we are gonna originate at hex 3000, like all the other programs. So when you look at the equation, so let's come back up to Shrage's method. This, right? We see that we have to represent x of n as a times x of n minus 1 mod m. So you have to bring in what a is, right? What this is and what this is. And then at some point you would have some of the other variables. So this is why we want to start with loading a. So I'm going to load a to register 2. Then I'm going to load m to register 3 because these two are part of the equation. Okay. Now, when you do this, what you need to do is you need to think about how in programming, how we handle the priority in arithmetic. And on the low level, we have to address that based on the priority, right? If you learn C++ or Java or programming in general, we talked about how certain arithmetic operator would be used first. So here we're going to do the mod m. So that's a division. And then we would handle, right? So sometime, so the procedure for this, what we want is we want to be able to take the m value and be able to apply the mod to it. So here is where, this is why we call the division function, or we jump to subroutine div. But also there was information about this part. Okay. So we need to be able to show what this part is, right? And Q is going to be M divided by A, and R is going to be M mod A to implement this right here. Okay, so we are working with this right now. So right now, so it's going to return your Q and your R. We're going to talk about the div in a little bit. So this is like the main section in C where we would call the function, right? And we would initialize our variable and all of that. Then we're going to store the Q from register 4 and store the R from register 5 because that's coming from the that's coming from the function or the subroutine. Then we're going to load X to register 3, Q to register 2. And then we're going to divide. So we're going to call on the division function or jump to subroutine div. Right now, at this point, you are going to do X divided by Q. So here in this part, right, what am I looking at? This part right here. So A times X mod Q minus R, right? We implemented this. Then so after the division subroutine or div subroutine, I am going to store, right, my return value to x div q and from register 4, and then from register 5, I'm going to store that out to x mod q. Then I'm going to load register A register 1 with A. And then I'm going to load x mod q to register 2. And right now, what we want to do is we want to call on the function to multiply. So jump to subroutine mult. So let's flip back to this, right? We're doing this part now. So earlier when you did the div, that was for this. And now you need to do this part. Okay. So after we have it multiply, right, we would take 0, add it with register 3, and then put it on register 4. So here is when we copy. So register 4 would have A times X mod Q. Then I'm going to load R to register 1. And load X div Q to register 2. Because I want to get ready to take R times X divided by Q. Okay. Because previously we already have the division for X div Q for what's inside the parentheses, right? And I can't emphasize much about, so in the prior lab, all of that, we talked about how we handled the inside out first. So that's what we did right before this. And then after that, now we're going to use the function to be able to multiply the result from X divided by Q with R, right? That's why we load R and we load X div Q. And then at this point, we are going to call on the function or to jump to subroutine mult to multiply. So your register 3 should have R times X minus Q. Then we're going to do the 2 complement of register 3. So coming back here, right, you have to subtract R times X minus Q. And right now, this part is in register 3. So we are going to have to do the 2 complement and then we add everything together for this condition.
Is it in register 3 because that's where a subroutine is putting it at?
Yeah, earlier because for the definition for the subroutine, we use that register. So it's returning and from that register, we had store from 4 to 5 to a label, right?
Okay,
but yeah, if for, you can basically use any register as long as it's the register that's returned from the function. And if it's not, you can copy.
All right, cool.
So we have to handle the subtraction of R times X minus Q. That's why we did the 2 complement, right, of register 3, because register 3 has R times X minus Q. Then we are going to take all of that, the negative of R times X minus Q, and then we're going to add it with register 4. And register 4 has A times X mod Q, if you recall from the previous section. So now we have that first part of the condition, the if, in register 2. So I put the comment there for you. Now, if you're looking here, right, it says if X is greater or equal to 0, then we would have this part of the equation. So we already did that. So now we just got a branch for the if. So we would take what's in register 2, and we would check. If it is 0 or positive, we're going to send it to skip. So if X is greater or equal to 0, then skip. Then now what we're going to do is we're going to load M to register 1. And we would take register 2, we're going to add it with M. So what am I doing here? This part, the else. Okay. Because we already have register 2 as A times X mod Q minus R times X divided by Q. Now we got to add the M for the else. So once we're here, we have the else part, right? Because if you think about the logic in this, we already have the if where we send it to skip, right? If it doesn't check true for that, it's going to execute the else here. And so as we did the skip, then we're going to store X from register 2. And this is going to be the start of your empty stack. Now we're going to start working with stack. Okay. So before you begin your stack, you got to load it to your pointer, right? The document already show you how you can do that. So I have a base, which is tied to an address, and I load it to register 6. And then I'm going to take X, as I stored out from earlier, I can load it to register 3. For the stack, because I previously used register 2 for skip, right? I'm going to go ahead and clear it so I can reuse it. And I want to add 10 to register 2. The reason why we're adding 10 is because it is a decimal value, so we're going to mod 10, right? For your integers. So I would take 10, I would add it to register 2 and put it on register 2. So register 2 has 10, decimal 10. Then I operate the division by jumping to subroutine div. So this is going to allow me to have the decimal value. So because the way that we use this is numbers are going to actually represent decimal numbers. So you have to make sure that it's applied to its system by using modulus of that particular number system, right? 10. Then we're going to take 0, we're going to add it with register 5. So we're going to copy what's in register 5 to register 0. Remember that the assignment ask us to take from what register 0 and push. Okay. Then at this point, the value that's returned is from register 5, right? You copy it to register 0. And then you are going to push it onto the stack. Then you're going to take what's from register 4, add it with register 0. You're going to copy the content of register 4 to register 3. Here is where it's going to check for positive, right? If it's positive, it's going to go back and add it to the stack. So if positive, go to stack. Else, it's going to continue. Now on the next section, this is going to be unstack. Okay. Or you can call it, because I already have a pop subroutine, so I don't want to call it pop here. So I have to say unstack. So for the unstack, I want to begin with jump subroutine and is empty. So Remember that we would only pop if it is not empty. So I want to check to see if it's empty or not. So therefore I have to call the function is empty. Right, so is empty subroutine. If it's 1, then I'm going to continue. So branch to cont. So if it's positive, go to cont, else keep going. So if it is empty, right, I would check for positive, then go to cont. Then after that, I'm gonna call the subroutine or jump to subroutine pop. Okay, so you want to check the stack to see if it's empty or not. If it's not empty, you will pop. And then after you pop, you want to ASCII convert. So I would jump to subroutine decode and then output. So here at this point, you want to keep your register 0 consistent throughout. So that way you don't have to copy register, because it can only output from register 0. So I gotta make sure that register 0 have the value that I can display on the console. So this one, you don't have to set value, right? You just need to check. You just need to run on the console. So it should show up on the display. Then I have an unconditional branch back to unstack. So it's going to come back. Again, it's going to check for empty or not, right? And if it's not, it's going to pop and then decode and output. As we used cont earlier, we got to define it now. So I'm going to load the label space to register 0 and then output. And then I'm going to load LC to register 6. And as you learn in the document for the lab, we talked about how stack goes downward. So we're going to move register 6 down plus add -1. And then we have to store it to LC. Then it's going to, so next we're going to check to see if it's 0 positive, right? And it's going to loop until it's negative. Then we're going to halt. For the space, I wanted to fill up with decimal 10, so you can fill. And then X, we want to fill with decimal 100. And at the beginning, we learned that A is initialized at decimal 7. And M is initialized at decimal 32767. For the Q and the R, they're arbitrary, so we can fill it at 0. And the same thing with the div Q and the mod Q. For my stack base, it begins at hex 4000, and the LC is going to be decimal 20. This is your loop counter, right? And as you loop, it's going to subtract. So we want to be able to generate a certain amount of numbers, so it's going to keep looping. So your loop counter, you can fill it at 20. And then the next part, we just need to add our multiplication and division functions, or the mult and div subroutine. And so very similar to what you've seen in the last lab and the prior, right? Here we are using register 3. Remember earlier we were using register 3. So you're going to clear register 3. We would take register 1 and add it with register 3, right? Because when you multiply, you have a multiplier, right? A value that you're multiplying with. So you would add the value and you would send it through the loop, right? So many times, and as you do, you will count down on the loop. So it's gonna repeat, it's gonna keep adding itself. So if I have 3 times 5, right, I wanna take 3, adding it 5 times, and every time I add, I gotta count down 1. So it's gonna branch, as long as it's positive, it's gonna keep looping. Once it's not, right, if it gets to 0, then it's done. So we have a return. And then your division, we would save register 2 and register 3. So save 1 and save 2 here. Clear register 4, we would do the 2 complement of register 2 because you have a number dividing by another number, so you would have the divisor, right? And that's basically subtraction multiple times for the division. So you keep subtracting values. So here is where your loop, you clear register 5, you add 4 with 1 and put it on register 4. And so then you would copy register 3 to register 5. So that way we can combine for the division here. So basically we would take this divided by this, or basically subtract it many times. And as long as it's 0 positive, we will keep looping. So it's going to keep subtracting until it reaches negative. And then each time we would count down and return. So when you use the label for temporary safe register, you can fill it with hex 0. Okay. Any questions so far? Then after that, what we're going to do is we are going to use the push and the pop. So your push, we're going to take 6, we're going to add it with -1 and put it at R6. Remember, this is our push meter. Push down. And then store it. So store it to register 0 or copy it to register 0 and then return. Then we're going to load register 6 to register 0 for the pop. So here is where we load. And you notice the difference. So when you push, you store, right? When you pop, you load. But for push, you subtract 1 as it goes down 1, and then store and then return. For the pop, you are going to load it first and then add 1. Right, it got to move back up to the address and then return. Okay, this is what you've seen already in our lecture, and then also for today example in the lab document. Then you have is empty. And sorry, my tab on Word is a little bit off, but it should be like nice and neat, like what you've seen on the screenshot. So is empty, we're going to load empty to register 0. And then we would add register 0 with register 6. Why? Because this is your meter for your stack, and this is where the label is. And so we want to check to see if it's 0 in register 0. So if it is, then we're going to send it to is. Then we're going to add 0 to it, which basically it is itself on register 0, and then return. Because it's empty used right earlier to check our stack. Then for the is, since we branched to it, we're going to clear register 0, and then we're going to do the add 1 to register 6, right? Because when it's empty, then it's positive 1. So yeah, so we add the 1 and then return. And for the empty label, we're going to fill it with hex C000, which is negative hex 4000. For the decode, this is simply, I use the decimal, but you can use what's in the document where they use the hex. So I decided that most of my stuff is in decimal, so we'll stick with decimal just to make it less confusing. So here is where the ASCII conversion happens, right? I add 15 to register 0 and put it on register 0. It must be register 0 here for the decode because we're going to output from it. That's the only register that's going to output. So we add 15 3 times, which gives us 45. And then we add the 3 to make it 48. Then we're going to return, and that's going to allow us to output the values as characters on console. And we're going to do the .n. So this one, unlike the others, you have data kind of fill throughout. If you want to keep the data separate, you just got to flip it back and forth. So we kept the data kind of in its section so that way we can track it. But if you prefer for the data to be later in the program, that's fine too. Okay, but you can also do it this way. Traditionally, we normally keep the fill at the end so we can see, but you know, it's not absolutely required like that. But by practice, they recommend that you put the data in its own section. Okay, so once we have the program, we're gonna assemble it. So give me a second. Sorry. Okay. Then assemble. Once you have no 0, and then if you're using the online, you can paste the code on there and use their assembler to be able to assemble the program. Once you have your object file, you can simulate. So take the simulator, right? We're gonna go ahead and open our OBJ file. And then just run. So here, you should have the numbers randomly. And if you look, right, there should not be repeating values. So to really test it, if it's random, right, if it's truly a random generator, you are going to have a different set of values on the next execution. So let's try that again, right? So we can stop because this is infinite loop. So you have to stop it. Oh, I'm sorry. Yeah. So what we can do is, let's see if it's, let's reload it. So reinitialize your machine, open the file again, and then rerun it. Okay. So you can take screenshot and compare and see if it's different or not, right? Usually pseudo random generator, if you're seeding from the same point, you are gonna get pseudo random. That means that it's gonna look random, but they're actually the same values because it's the same seed. Now, truly random generator, it uses system time, and every time you run is different. So if I run a minute earlier, right, like let's say 6:52, and then I run another program at 6:53, it's different time. So it's going to seed it at system time. So you're going to have different values. And so a true number generator that is random, a true random generator, it uses system time or an environmental value, right? That is different all the time. So that way you're going to get different values as output. So many of the random generator that you see are actually just pseudo random. They're not true random generator. A true random generator apply an environmental value, like I said, such as system time value that you can use. So in my advanced Python class, I addressed that, and you can implement that. If you work with Linux, right? If you program, for example, if you use Java or Python in Linux, you can incorporate, and yeah, there are libraries that you can use just to bring in system time and use that as seed. And then once you have that seed value, you will be able to just apply it with the function and be able to generate values that are going to be different every single time. Okay. So when you examine the library that says random, you kind of have to look at their code and see, is it truly random or is it pseudo random? Okay. And pay attention to where it's seeded. So if we apply a certain seed value, then that's fixed, that's a constant, that's the same every single time, then it's only pseudo random. Now, in order for me to have more values, let's say that I want to generate 100 values instead of 20 or 10, then all I have to do is to be able to look at how my generator function is created. If it's using a loop, I would need to modify it. If I'm storing it to an array, I also need to change my container. So the question for the lab is for you to go back to the code and look at how you can change the output to a less or more values, right? So how will you be able to do that? So look at the code on how you generate the value, okay? And what kind of things you need to change to make sure that you update it so that way it would display more instead of just what's asked. Any questions? Okay, so don't forget to answer the 2 questions at the end after you assemble and run the program, right? So I already give you the code. You just have to go through and understand it. And that's my way of asking you to go back and look at it, okay? How can you modify it to be able to have more random numbers display? Okay. Any question? Okay, since we have time, I'm going to talk a little bit about next week. I'm scheduled to present at the Board of Trustee meeting next week. So I will not hold class lecture on Tuesday, which is the 2nd, right? Because the meeting starts at 6 and it's going to go to like about 8:30. So it's going to overlap our time. What I will do is you can use that time to be able to work with your team members, or if you have decided, if not, you can start thinking about your project or catch up with work, whatever you want. What are we going to go over the in-class assignment, the code for question 10? Is that for this week? Is that what you're asking? You have to come up with the question 10 code. It's very close to question 8 or 9. So you have to be able to use what I had explained and given to you because at this point, we should be able to come up with our code based on the example. Okay. Yeah, so on Tuesday, there will be no session, so I will send an email for that. On Thursday, because this is one of the last lab that we're going to be doing. So on Thursday, I will do the lecture. For the following week, I'm going on the field trip, so I do plan to do some, final review down the line. So what I'll do is I will send out email and announcement on Tuesday just to remind you in case you forget. And I keep it recording so that way for the people who are watching later on, if they didn't attend class today, they would be able to remember. So on this Tuesday, or the next Tuesday, we're not going to have the regular session, so you can take a little break and then start thinking about your project if you need. And then on Thursday, what I'll do is I'll go over the lecture on Thursday. Okay. And then if you, for the lecture, I had posted the video and there was question about number 10. So use the prior exercise and you should be able to write number 10. There's only a small slight modification, so it's good. That's a good question. Okay, let me stop recording.